Marine pteropods, or sea butterflies, are found throughout the ocean and are a major food source for fish and other organisms. In laboratory experiments, this pteropod shell dissolved over the course of 45 days in seawater adjusted to an ocean chemistry projected for the year 2100. What changes in the ocean might be putting pteropods at risk? The burning of fossil fuels has caused levels of carbon dioxide in the atmosphere to rise. This carbon dioxide, or CO2, doesn't just stay in the atmosphere. Roughly 30% of it is absorbed by the ocean. When CO2 reacts with water, it forms carbonic acid, which quickly releases a hydrogen ion, or H+. The more hydrogen ions, the lower the pH, or more acidic a solution is. As CO2 levels increase over time, seawater will progress towards the acidic end of the pH scale, a process called ocean acidification. We can make projections of this change in the ocean pH over time. It is expected that later this century, if CO2 emissions continue at the current rate, the average pH of the ocean will drop from 8.2 to 7.8. This relatively small decrease in pH may not seem significant, but it could impact many species of marine life. For pteropods, corals, and other species that depend on shells and exoskeletons, ocean acidification will lead to a decreased availability of dissolved calcium and carbonate, the chemical building blocks they use to make their shells and skeletons. If ocean chemistry changes as expected, shells with calcium carbonate mineral structures may begin to dissolve, depending on where they live in the ocean. How do we know that ocean acidification is happening? Scientists at NOAA and across the world have measured these chemical changes over the past 40 years during research cruises, taking hundreds of thousands of ocean water samples. Shown here are the results from cruises in 1991 and 2005, where the availability of the shell mineral was sampled. In both years, the highest concentration of available shell minerals were found in the surface waters, as shown by the dark yellow colors. Deeper waters naturally have very low availability of these minerals. However, when we look at how these values have changed between 1991 and 2005, we see that the availability of the shell mineral decreased much more in the surface waters, as indicated by the blue colors. In other words, ocean acidification is impacting shallower areas much more than deep areas. Shallow waters are where the bulk of the ocean productivity occurs, including the most diverse and economically important species and habitats. And these changes aren't occurring in just certain parts of the ocean. They're occurring throughout the entire ocean. Today, repeated research cruises and permanent sampling stations continue to monitor changes in pH and availability of calcium carbonate minerals. As the ocean approaches a critical transition between shell building and shell dissolving, food webs in the world's oceans could be impacted. Phytoplankton and zooplankton, like pteropods, form the basis of most oceanic food chains. Coral reefs form the foundations of the most diverse marine habitats, and shellfish, such as oysters and crabs, and finfish, such as salmon, support economically important fisheries in many of the world's coastal communities. People depend on the viability of these species to ensure a healthy future of our own.